Good afternoon, everybody. Hope you're all having a good time. Good afternoon. Everybody awake? I know it's late in the afternoon, right? You guys want to get your drink on soon, but not quite yet. I'm going to spend the next little while talking to you about Backhaul, and in order to, this is based primarily on the material that I put together for the CWDP book, which is on sale now, so make sure you go buy a copy. I decided to kind of make it a little more fun. Back in June, I did a webinar in conjunction with Ekahau talking about mesh, and we called it To Mesh or Not to Mesh, and we did this whole Shakespeare theme on it, and I decided I was going to extend that for this presentation. So today's talk is Much Ado About Wireless Backhaul. I've really got to thank the folks at Ekahau for this picture. They did a great job putting this together for me. So a little bit about me. I am a veteran in wireless backhaul. I designed and I got into this industry in early 2008, working for a startup company doing Wi-Fi primarily in apartment buildings and other multi-dwelling unit environments. My first 2 weeks on the job, they sent me to Sugar Grove, West Virginia to debug a mesh network. Now I know Tom's not allowed to answer this, but does anybody else in the room know where Sugar Grove, West Virginia is? Basically, you go to the middle of nowhere and hang a left. 2 weeks onto the job, it's like, here, deploy a mesh network. Spoiler, self-interference, which we'll be talking a little bit about today. I've since then worked on dozens of mesh networks as well as other, probably several hundred now, point-to-point and point-to-multipoint networks over the last 10 years. My current role is Director of Business Development at LegalWave Networks, which is based in suburban Atlanta, and we do Wi-Fi and we do point-to-point and point-to-multipoint. Our specialty is point-to-point and point-to-multipoint. So that's what we're going to be talking about today, is the different forms of wireless backhaul, when you should use them, when you shouldn't use them, and so forth. And of course, going with the Shakespeare theme, the slides are all going to have Shakespeare quotes. Some of them are going to be a little bit adapted to Wi-Fi. Oh God, I could be bound in a mesh network and count myself emperor of infinite bandwidth, were it not that I have bad dreams, from Hamlet. So when you approach wireless backhaul design, it's like approaching any other type of Wi-Fi design. I got to look at my requirements, so I got to look at usage, I got to look at coverage, I got to look at capacity, I got to look at control and monitoring, and I got to look at how I'm going to integrate it, what my infrastructure is going to look like. So, right, straight stuff that you would do for any Wi-Fi network. It also applies to any type of wireless backhaul. And I got to look at my constraints, right? What are my budget look like? What are my aesthetics? Mounting and wiring, right? Electrical power, any other restrictions that I might have on my network. There is no darkness but ignorance. So, understand your design parameters and your design goals. Right? So what are the knobs that you have when you're doing a network design? What are the things that you actually can change and have choice over? Well, the first thing you could do is, what AP am I going to use? And if you're using an AP with internal antennas, which is very common in both Wi-Fi applications as well as point-to-point and multipoint, you're picking the antenna when you pick that model of AP. You have a choice, subject to your constraints, of course, as to where you put the APs. Now, if you're doing something like a surveillance network, right, that might be dictated to you by, say, where do you need cameras, right? Because that's going to dictate where I got to put the Wi-Fi access points. I got to put them by the cameras. I have control over the channel, or channels that you're using if you're doing dual band, and I've got control over the transmit power. Your design goals, I want to maintain functional independence, right? Which means I want to actually maintain my usage requirements, my capacity requirements, my coverage requirements as independently as possible. I also want to minimize complexity, which is something that we're very bad at in this business. Anybody who heard my talk yesterday on AX when I was up here with Devin knows that what we do as an industry is we like to make things more and more complex in order to stuff the channel with more bits. But when you're doing a Wi-Fi design, I want to keep it as simple as possible, so that it's easier to debug and troubleshoot. And I found a great Shakespeare quote attributed to design. See first that the design is wise and just, that ascertained, pursue it resolutely. Do not for one pulse forego the purpose that you resolved to effect. In other words, keep your eye on the prize. So, when we talk about wireless backhaul, there are several different types of wireless backhaul. I've got my conventional wired APs, right? This is your traditional, I take in a normal dual band AP, I plug it into a switch. That is a form of backhaul. What am I backhauling to? I'm backhauling to a tablet, a PC, right? A phone, right? Some type of end client device. But that's certainly just the first way of doing wireless backhaul. I can do a client bridge, right? Which is basically turning a wired Ethernet NIC into a wireless Ethernet NIC. I can do a repeater where I'm repeating the signal from one AP to the next. I can do point-to-multipoint bridging, and I can do mesh. Now, in this diagram that I've got here on the right, I've got examples of all 5 of those. All the world is a network, and all the APs and clients merely players. They have their exits and their entrances, and one AP in its time connects many clients. Shakespeare was indeed ahead of his time. So when you approach wireless backhaul design, whether it's Wi-Fi or whether it's another type of backhaul design, one of the main goals is to avoid self-interference. Now, the problem with trying to avoid self-interference is that when you're using things in repeater mode, or you're using things in point-to-multipoint mode, or when I have a mesh group, those radios all have to be on the same channel in order to intercommunicate with one another. But every time an AP communicates with client devices, you're consuming airtime for all of your neighboring APs. So that self-interference just further lowers your airtime capacity, or sorry, just airtime, perhaps, after Joel's talk, by causing more retries. I'm not going to read out the whole quote, but this is a nod about the ghost frame. It's from Hamlet, where the ghost frame roams the earth at night and haunts the living, and I'll read the last bit. I could show you RF interference that would slice through your soul, freeze your blood, make your eyes jump out of their sockets and your hair stand on end like dipole antennas. But mortals like you aren't allowed to see RF waves in the air. Although, I don't know, maybe Sidekick version 2? So let's talk about a conventional, types of wireless backhaul, a conventional wired AP network. Right, what does this do? It connects wireless clients to a wired network. That's what we're doing in a conventional Wi-Fi network. A wireless device only has a single hop onto the wired network, right? That's the connection between the client device and the AP itself. Each AP, whether it's single band or dual band, is wired into a PoE switch for both power and network connectivity. And the APs can either be managed centrally or they can operate in standalone mode. And in keeping with much ado about nothing, I would my Wi-Fi had the speed of your tongue, and so good a continuer. Best practices for wired APs, right? For those of you who've done any design work, place your APs as close as possible to the client devices. Why? Because clients have weak transmitters, and they tend to be not quite as good receivers and transmitters as your client devices. I'm not designing the APs for their ability to talk. I am designing for the client's ability to talk back. Similarly, I want to place the APs as far apart from each other. So I want as little distance and I want as few things that attenuate the signal between my AP and my client device as possible. And yet I want as much distance and as many things attenuating the signal as possible between neighboring APs. Why? So I can reuse channels. Set your channels and your transmit power properly. Facilitate how the network's going to get used, right? So you need to know client types, you need to know coverage areas, you need to know your user densities. Remember my requirements list from before? Those are your main requirements. There's something roaming in the state of Denmark. It turns out it's Helga. So thank you, Anders, for the photo of a recent trip that the Wi-Fi moose made to Denmark and visited with Hamlet. So let's move on beyond Wi-Fi to other modes of operation, the first being a client bridge. right? Where we're connecting, remember, in conventional Wi-Fi with conventional wired APs, I'm connecting wireless clients to a wired network. Here, I'm connecting wired clients to a wireless network. So I'm basically taking the AP and I'm running it in reverse. These used to be called gaming adapters and were sold for very, very high prices for Xboxes and other gaming consoles, right, back in the day when they just had Ethernet ports in them. Now, of course, they all have Wi-Fi in them. But what a client bridge does, it converts a wired Ethernet connection into a single band wireless client connection. And then the client bridge itself is a Wi-Fi client, and it connects to an access point as a wireless client device. Now, the problem with running things in client bridge is that it's really designed for a single device that's plugged into the Ethernet. Because if you plug in multiple devices into a client bridge, the rest of the network is only going to see one MAC address, which is the MAC address of the client bridge itself, which can make it very hard to debug things. Say if I actually plug in a switch into that client bridge and then hang like a whole bunch of cameras or other devices off of it. Client bridges are almost always configured in standalone mode. They generally cannot be centrally managed. Once more onto the breach of Wi-Fi, dear friends. Next mode we have for wireless backhaul are repeaters, right? Now, nobody in this room should be using repeaters, correct? Correct? Okay, how many of you use mesh networks, though? Anybody? Anybody? Nobody uses mesh networks in here? Nobody? All right, I see a couple out there. Guess what? You're actually using a form of repeater. But we'll get to that. So, what does a repeater do? It connects wireless APs and client devices to a wireless network, right? We're going first wireless to wired, right? Then we were going wired to wireless. Now I'm going wireless to wireless. The problem with a repeater, of course, is that it's doing double duty. It's spending half of its time talking to wireless clients downstream, and it's spending half of its time providing backhaul upstream. So what that means is that you're losing 50% of your bandwidth, and if you happen to have these things strung out 2, 3, or 4, you're losing 50% of your bandwidth per hop. Where do you want to use these? You generally only want to use them in non-enterprise environments, right, to fill coverage gaps. Repeaters are usually configured in standalone mode. So modern APs can actually be run as dual band APs, where on, say, for example, 2.4, I set it up as an access point, and on 5 gigahertz, I set it up as a repeater. And I have seen APs that do that. Why? And Faith methinks the Wi-Fi signal is too low for a high praise, too spotty for a fair praise, and too slow for a great praise. So if I do need to interconnect things wirelessly, I really actually want to start looking at point-to-point wireless bridges. Remember, we were talking about connecting wireless devices to wired networks, connecting wireless devices to other wireless networks, connecting wireless to wired. Here, you are actually taking two wired networks and I am connecting them together wirelessly. The AP acts as a wireless wire, which apparently is a term I can't use anymore because a vendor who shall not be mentioned is actually now using that as a product name. But this has been a term that we've been using in the industry for years to talk about point-to-point and point-to-multipoint bridges. Basically, what happens is from both sides of the link, it looks like you have a wire going across. All of your layer 2 information is preserved. So all of your MAC address information is preserved. All of your VLAN information is preserved. And what happens is that the Ethernet frame itself is fully encapsulated, encrypted, put in a wireless frame, transmitted wirelessly across the link, stripped out of the wireless frame, decrypted, and then passed on to the wireless network, onto the wired network on the other side. These are usually single band APs. And in the past, traditionally, these have been configured in standalone mode. However, some vendors are now able, including the company that I'm working for, are now able to do cloud monitoring and management of point-to-point and point-to-multipoint networks, which is really useful if you have a whole bunch of these deployed across multiple network sites, to be able to manage these from a central controller, just as we're used to monitoring Wi-Fi from a cloud controller. Your antenna, sir, would cure deafness from the Tempest. So let's talk a little bit more about what we mean by point-to-point versus point-to-multipoint. For point-to-point, right, I'm connecting one unit to one unit. It's one point to one point. If I have neighboring links, they need to be put on independent channels. In point-to-multipoint, I'm connecting one point to several general subscribers. We generally use the term base station and subscriber to talk base station as the point, subscriber as the multipoint. All the links in a point-to-multipoint group will share the same airtime because they have to be on the same channel in order to intercommunicate. Neighboring point-to-multipoint groups, so if I have a group going that way and a group going that way, I need to put them on independent channels so that they don't interfere with each other. Words are easy, like the wind. Faithful subscribers are hard to find. So a typical wireless distribution system, and that's the term we generally use to describe a point-to-point or point-to-multipoint network, would look like this. I can run in a couple of different modes, depending on the vendor. Some vendors will allow you to do what's called a WDS bridge mode. So the endpoints are all configured standalone. They're configured identically. However, you're basically specifying the wireless LAN MAC address of the radio on the other side in order to connect to the APs. I can also run these in what are called access point and station modes, which is much more analogous to configuring a conventional Wi-Fi network. So the access point actually broadcasts an SSID with encryption, and the stations are basically clients. So from that perspective, it looks just like a normal access point network. The difference is, of course, it's preserving all of that layer 2 information between the access point and the station. And that's the main difference here in this mode versus just a conventional access point and client bridge. Nice thing about this mode is that it's actually scalable to large numbers of subscribers. And in typical WISP applications, especially in rural areas, you might have 30, 60, or even 100 subscribers connected to one base station. Love all clients, trust a few subscribers, do wrong to none. Now, some vendors, such as LegoWave, actually specialize in point-to-point and point-to-multipoint. Generally, vendors that specialize will have dedicated AP models. And these models generally will integrate directional antennas that are intended for point-to-point and point-to-multipoint applications. Many times they'll include hardware acceleration for quality of service, so that both in the hardware and perhaps also in the software, we're prioritizing voice video traffic over non-real-time data traffic. Very often, these types of access points are actually not using the 802.11 protocol. They will be using the 802.11 chipset, but they'll run a proprietary wireless protocol. These may or may not be TDMA-based. Many vendors do a TDMA-based model. Some vendors do a kind of a token type of model. Generally, there are QoS modifications that are proprietary to that vendor. And the purpose of doing proprietary algorithms and a proprietary wireless protocol here is to strip out a lot of the CSMA CA stuff and other Wi-Fi overhead so that it becomes a little bit more deterministic and the link will actually run faster than it would under straight WDS. Many vendors in the space also provide design and installation tools, as well as now centralized cloud management for point-to-point and point-to-multipoint. Some are born great, some achieve greatness, and some have greatness thrust upon them. So here's an example of a typical point-to-multipoint network for small and medium business applications. Typically for a WISP application, I can put up a tower, a nice tall tower somewhere that gives me a good view of everywhere that I want to hit. But typically in a small, medium business application, such as a residential neighborhood, towns don't really let you put up towers. I can't put up a 100-foot tower in the middle of a residential neighborhood. For some reason, they frown upon that. Don't know why, but typically what that means is you've got to find clear paths because there are going to be buildings in the way, so I don't necessarily have line of sight to everywhere that I want to hit. And the way that we generally approach these designs is that we have a standard set of components, and then I tailor those components to meet the specific needs of a property. So this is an example that we recently did. We had 9 camera locations that were spread out throughout the property. The MDF, where the NVR, where the network video recorder was located, was in the middle of the property. There was very limited line of sight between buildings, and we wound up doing this actually with 16 APs. And you could see some of them actually have 3 hops in order to get to some of the cameras. Now, anybody realize a potential problem with this design? Right, I told you we had 3, if you wanted to reach, for example, cam 7 in the lower right-hand corner, right, I need to have 3 hops. I've got the green hop, I've got the light blue hop, and then I've got the purple hop. Every hop introduces latency. This is a surveillance application. Surveillance error, right, those latency delays stack linearly. Typically, when we're doing wireless surveillance, we generally try to keep it to 3 or less hops. The reason why is because of latency. It's not even so much because of the camera. Though typically, in my experience, high bandwidth cameras tend to be even more sensitive to latency than lower bandwidth cameras. That just seems to be how they work. Different cameras from different vendors will also behave very differently in terms of their tolerance to latency. Another issue, you can't always get line of sight, right? In this example, the initial design, they said, oh yeah, the building in the middle where the MDF is 3 stories tall, everything else is 1 story, there are no real trees to worry about, you got line of sight to everything. So we designed it that way. Turns out you go on site and yeah, that's not true. The MDF was 2 stories, all the other buildings were 2 stories, and there were trees everywhere. And of course, I didn't have line of sight to most of the places that I needed to hit. So then I've got to set up relay points, right, in order to hit all of those locations. Usually I'm going to try to pick locations that already have cameras or that I already have to hit anyway. So I'm not establishing additional links to buildings that I don't already have to provide service to. And we can use that to accommodate the line of sight issues. Now, in the direct example, I had 32 APs. Here, we need to do 38 APs. So the number of APs actually didn't even go up by all that much, 20%, which for this many cameras actually really isn't a lot. But the design, of course, is a lot more complicated. Another useful application for point-to-multipoint is elevators. So modern elevators in newer buildings have Cat5 cables that are part of the runner. So there's a Cat5 cable already going into the elevator cab. Older buildings won't have that. And apparently to retrofit such a cable onto an old elevator that doesn't have it is ridiculously expensive. But it turns out one of the very nice things that you can do with point-to-multipoint is, even though point-to-multipoint we typically think is fixed wireless, right, going from point A to point B and both points are fixed, the links will actually because Wi-Fi is designed to be mobile, the links will actually dynamically adjust for the fact that the elevator is moving up and down over time. So you can put one access point at the top of the shaft. I can put the subscribers on each elevator that's in the shaft. And away you go. And then as the elevators move up and down, I'm dynamically adjusting for the distance. Elevator shafts tend to be big steel boxes, but it turns out that MIMO actually helps you with all of those reflections. In fact, one of the biggest issues with this is that typically for your directional antennas that you're using for point-to-multipoint, your gain is actually too high, and even when you turn the power way down, it can often still be too high just because, remember, these are links that are designed to often go a couple of miles, and here I'm going a few hundred feet. So let's talk about mesh. Everybody's favorite subject. So what does mesh do? It provides Wi-Fi service to clients as well as wireless backhaul to an AP. Right? When I can't get an Ethernet cable to an access point, I'm going to let one of the radios provide that backhaul. Mesh is kind of like an automatic repeater, so it's like a combination of point-to-multipoint and repeater. And there are a couple of different ways that you can run mesh, so that acts more like one or the other. You can, in some sense, think of mesh as scalable repeaters, because a typical repeater is one device that's configured in standalone mode, whereas with mesh, the access points themselves or the controller, depending on the vendor, will actually try to calculate an optimal path through the network and will adapt to changes in the environment. So if one AP goes down, the APs that are behind it will actually try to find another path back to a root node. It's intended for large networks where wiring is either impossible or just cost prohibitive. But it has some challenges. What a piece of work is mesh, how noble in reason, how infinite in faculties, in form and moving, how express and admirable in action, how like an angel in apprehension, how like a god, the beauty of no wire, the paragon of backhaul. Now, for those of you who are familiar with Hamlet, when he gives this soliloquy, you know he's being incredibly sarcastic, and so am I. So let's talk a little bit about mesh network terminology. You've got root APs, so these are your APs that actually have a wired connection to the wired switch infrastructure network. And I put wired here in quotes because your wired connection may be a wired connection into a point-to-multipoint link on hopefully a different channel if you've done your channelization properly. But this is an AP that's using a quote-unquote wired connection for backhaul. Versus a node AP, which does not have an Ethernet connection except perhaps for power. And so it's certainly not using the Ethernet for backhaul. And so I have to do the backhaul wirelessly, and I can do the backhaul to either another node AP or back to a root AP. And again, each wireless link is referred to as a hop. Now, when I started off in 2008, 2 weeks into my first job in Wi-Fi, we were using single band APs for mesh. So had to just use it in single band repeater mode. So half the time it was servicing clients, half the time it was providing backhaul. Guess what else? Because they all had to see each other, they were all on the same channel. Every single AP in the network was on the same channel. And it was not a single channel architecture network. Though I had to run it as a single channel architecture network. So guess what? Massive amounts of co-channel interference. When you use dual band APs, generally you're using the 5 gigahertz radio for simultaneous wireless backhaul and client access, and then the 2.4 radio is usually only used for client access. In which case, obviously, I can channelize my 2.4 and my 5 gigahertz. Well, we'll talk about channelization about 5 gigahertz in a minute. Again, another quote from Hamlet, neither a node AP nor a root AP be, for node APs oft lose both itself and friend, and root dulls the edge of client performance. So, how does mesh work? It calculates the path. The remote APs will calculate the best path route through the network, adapting to changes in environment, such as APs going offline. There is the 802.11s standard for mesh, but everybody has a proprietary mesh algorithm. Every vendor that does mesh has a proprietary mesh algorithm. Typically, the things that you are optimizing is I want to minimize the number of hops to minimize latency. I want to maximize the signal strength. Right, so I want to select links that obviously have the strongest, right? I want to select the strongest links with the highest RSSI. And I generally also want to balance the load. So I want to account for the number of clients on each AP so that I'm balancing the load across the network. But there's a problem. Those parameters can be conflicting, which can lead to counterintuitive and suboptimal solutions. There are more things in mesh optimization, Horatio, than are dreamt of in your philosophy. So when I was doing mesh back in 2008, we were using APs from a company called Tropos Networks. Does anybody remember Tropos? It was designed for metropolitan Wi-Fi. I had an SE from Tropos tell me that their mesh algorithm optimized over 100 different parameters. I mean, it was wacky. It was really, really wacky. A few years later, I was using a different vendor to do mesh on a different project, and their software engineers told me that they were optimizing over 2 parameters, namely minimizing hops and the signal strength. So every vendor does this differently, and they do it very differently. Suffice it to say, the Tropos mesh algorithms actually tended to work a heck of a lot better, although sometimes they gave you some very kind of oddball solutions and very counterintuitive solutions. Now, right, the throughput trade-offs, a conventional wired network, right, I'm putting all of my wireless radio is actually dedicated to servicing client access, and all of my backhaul is being done over the wire. Whereas in mesh, I'm utilizing the wireless for both. So I'm reducing my throughput and client capacity. Looks like a repeater. And if you're unfortunate enough, like I was 10 years ago, to be doing this on single band APs, it is a repeater. My recommendation to you is to avoid mesh unless there's no other option. Mesh should be the last thing that you do in a design. It should not be the first. It should be the last. If I am doing something like an RV park, for example, where mesh has often been traditionally very popular in the past, the way that I do RV parks now is that I place the APs where I need them to go to provide coverage, and then I do point-to-multipoint backhaul links to every single one, so I can avoid mesh. You really should only use mesh in scenarios where two things are true. The first being I can't do Ethernet cabling, and the second is that it's really not performance critical, right? If I have to have an AP out, in some corner of the property and I can't get wiring there, but it's only got to service 3 clients to just check their email, fine, I can live with the 50% throughput loss, right? But then that depends, again, going back to your requirements and your constraints. You cannot, sir, take anything from me that I will more willingly part with all, except my throughput, except my throughput, except my throughput. However, if you do need to do mesh, do it right. One of the main problems with mesh networks is that they tend to be deployed very poorly, as I discovered 2 weeks into my first job in Wi-Fi. One of the things that you can do with mesh APs is you can cluster them. So my general rule is a minimum of 20% root nodes. And I want to space these out roughly equally throughout the property. So how do I create a root node? I can either run a fiber to it or an Ethernet cable to it if it's short enough, or I can do a point-to-point or point-to-multipoint backhaul link to it. If I need to create more root nodes, do more point-to-multipoint backhaul links. Your backhaul channelization, on the 2.4 band, I'm going to basically set, alternating 1, 6, 11 channel schemes, as you would normally do. On the 5 gigahertz band, right, remember every mesh cluster has to be on the same channel, so you will have co-channel interference within that cluster, but I can set each root AP and each wireless bridge link to static, non-overlapping channels, so that they're not so that neighboring clusters are not interfering with each other and that none of them are interfering with my backhaul network. But you set all your node APs to auto channel. So your node APs nominally should be 1 hop away from a root AP. They'll pick up the local channel. If that root AP goes offline, those node APs will then find another path to another node AP. Now they're maybe 2 or 3 hops away from another AP. But at least I'm limping along, even if I'm losing some throughput. Mesh, the undiscovered country from whose bourne no Wi-Fi engineer returns. So here's an example of an RV park where we did clustering with mesh. I know the picture's probably a little hard to make out because it's a rather large RV park. And always with these types of properties, the MDF where the internet's coming in is in one corner of the property. I showed you a couple examples before where they're in the middle of the property. That's the exception, not the rule. In general, it's always in one corner. And generally where the most critical application is guess where? In the opposite corner. But what you can do here is I can do a mix of access points and point-to-point links. So the red lines represent my point-to-point and point-to-multipoint backhaul links that start off in the lower left-hand corner and then span over to other parts of the property. And then each of the clusters, each are nominally shown in different colors on separate 5 gigahertz channels. And my node APs are set to auto channel. Now, one of the funny things about RV park, this is an older design that we had done a few years ago that was done with mesh. Not this project, but another RV project that I had worked on a couple of years ago. They started off doing it as mesh, and then all of a sudden, all of the users were complaining. Why? Guess what people in RV parks are doing? They're streaming Netflix in high def on iPads, right? So mesh is no longer, right? Everybody used to say, oh, it's RV parks, right? Yeah, you know, they're not using that much bandwidth. I just got to provide basic coverage. No, they are actually big performance critical applications. So I can't use mesh in those applications. Now, to do this design over again today, I would do everything point to multipoint to connect every single AP on this property. So, design tips for wireless backhaul: select the right technology, right? That's what we've been talking about the last couple of days, right? I've got 802.11ac wave 1, right? That's typically used for point-to-point and point-to-multipoint applications because all I need is 2x2, right? And I separate my streams horizontal and vertical polarization. Do I use 802.11ac wave 2? Right? You guys know my opinion on wave 2. Multi-user MIMO is dead. That's for Wi-Fi. I should note that Cambium has introduced a product, and they've just actually announced another version of their AC Wave 2 product that's actually using multi-user MIMO for point-to-multipoint. It's actually a very interesting product. And as one of their competitors, it's actually a very annoying product because they have it and I don't. AX, right? We've had the discussion, will there ever be client devices? But there's a lot of potential for doing massive point-to-multipoint in surveillance and in WISP applications where I have control of those subscribers and my base station, and I can potentially talk to multiple subscribers simultaneously, taking advantage of things like multi-user MIMO, taking advantage of things especially like OFDMA, where if each subscriber only needs narrow channels, I could use OFDMA in a fixed pattern, right? So I don't need to, where's Devin? I don't need to recompute OFDMA like, you know, for every client. Right? Once the clients are online, they're in fixed positions, right? That makes it nice and easy. If you could look into the seeds of time and say which grain will grow and which will not, speak then unto me, from the Scottish play. Select the right antenna in point-to-point and point-to-multipoint, and even in Wi-Fi coverage, right? You could use directional antennas. Higher gain gives you more focused transmit and receive, but you've got to look at your side lobes and your back lobes. Internal antennas, a lot of APs, especially that are specialized for point-to-point and point-to-multipoint, will have built-in antennas. Makes integration nice and easy, but it limits your choices. If I'm using external antennas, I can do high gain stuff for long distances, I can do horn antennas, I could do custom profile antennas, right? There's all sorts of options there. Bend your speech a little lest you mar your fortunes. Understand your link budget. I'm running a little low on time, right? We've had other people talk about free space path loss, right? Keep in mind that 6 dB loss as your distance gets doubled. Keep in mind your Fresnel zone, right? That area, and when you're doing point-to-point or point-to-multipoint, it's not just up and down, but you got to look at side to side, especially if I'm sneaking links between buildings and such. I got to look at it radially. I also got to look at earth bulge, right? The earth is not flat. So if I'm going more than 7 miles, I got to take that into account as well. When signals die, there are no packets seen. The heavens themselves blaze forth the death of wireless links. Interference is the enemy, right? We've talked a little bit about self-interference, which are from your own APs that's completely under your control, versus external interference, which is from your neighbors and you just kind of have to live with. Know your frequencies, right? 2.4 gigahertz and 5 gigahertz are infested with normal Wi-Fi. I love that word, infested with Wi-Fi. If it's not my Wi-Fi, but you're in my space, you're infesting my airtime. So properties that are infested with Wi-Fi, I'm talking about somebody else's Wi-Fi, not mine. But there are a lot of choices for unlicensed frequencies, especially when you're looking at some of these other backhaul applications. There's 80 gigahertz. We've spent a fair amount of time talking about 60 gigahertz, 24 gigahertz, 3.5 gigahertz, 900 megahertz. They're also licensed, maybe not for much longer frequencies, like 6 gigahertz. and 11 gigahertz. So in conclusion, understand your requirements and constraints. Select the right wireless backhaul for your application. And I hope Ian is still in the room because I'm glad I'm not the only Doctor Who fan in the room. So I will close with the Shakespeare Code from Doctor Who and Love's Labour's Won, which is the lost play. So I know I'm a little bit out of time, but thank you very much. If there are any questions, please come talk to me in the lobby. Thank you.